Okay, okay, good. Our second speaker for this session is Colin Reid from Newcastle, speaking about Abelian chief factors of locally compact groups. So please, Colin.
Thanks. Okay, so yeah, I'll be talking about locally compact second-countable groups. So here's the definition, but I think it's more instructive to give examples of these things. So any countable group with a discrete topology, countably based profinite groups, Lie groups, algebraic groups over QP, and so on. And the ones we saw in Stefan's talk, automorphism groups of connected locally finite graphs. So it's a huge class of groups. And we're a long way from sort of classifying anything, basically, in the world of l.c.s.c. groups, certainly when you get away from the connected context. So that's the class I'm talking about. Now, one thing we do have are decomposition results, saying that you have a certain kind of normal subgroup structure. So again, we saw an example of this in Stefan's talk, but I'll just mention a couple of theorems. So one by Capras and Monod is if you have such a group with no, sorry, there should be an assumption here that G is compactly generated. That's very important. So you have a compactly generated l.c.s.c. group, and it has no non-trivial compact or discrete normal subgroups, then every closed normal subgroup contains a minimal one. And moreover, all but finitely many of them are abelian. So originally they said there are only finitely many, but actually you can get infinitely many abelian ones. Okay, oops. And second thing is that for, again, any compactly generated l.c.s.c. group has a normal series, which is almost a chief series. So the factors are either compact, discrete, or they are chief factors, meaning that gi plus 1 over gi is a minimal closed normal subgroup of g over gi. So there's no closed normal subgroup between gi and gi plus 1. So we have these general structural results. And what I want to focus on is what we can say about the abelian chief factors or minimal closed normal subgroups, because it seems like a natural place to start. You know, you might think the abelian case would be easier than the non-abelian case. And so an obvious observation is that these things have to be topologically characteristically simple. So if you have a subgroup that's preserved by all automorphisms of the group, all as a topological group, then that has to be either trivial or dense. Otherwise, it would give you a normal subgroup anywhere this thing appeared as a normal factor of something else. Okay, so it turns out we can classify these things. Here's the list. So there are 5 families of topologically characteristically simple abelian l.c.s.c. groups. And I'll explain what each of these are in the rest of the talk. And moreover, each of them occurs as a chief factor. And most of them occur as chief factors of compactly generated groups. The exceptions are q to the n and q hat to the n. Those don't appear as chief factors of compactly generated groups, but they do of l.c.s.c. groups more generally. Okay, so that's the classification. So this slide summarizes how the proof works. So basically, we know that any characteristic subgroup is trivial or dense. So we ask, is it trivial or is it dense? And if we pick the right characteristic subgroups, we get a kind of decision tree, which ends up giving the classification. So is it torsion or torsion free? And then this one is, do all the elements generate a compact subgroup? Does each element live in a compact subgroup? and then is it connected or totally disconnected? And actually, most of the classifications was already there in the literature. The one exception was this last class here, where it's totally disconnected and periodic and torsion-free, where I couldn't find a classification out there. So I had to figure out how to characterize these groups. Okay, so let's go through the families. So first of all, we've got elementary abelian groups. So this just means that every element has order p for some prime p. The structure of these groups is very well known. I've just cited a textbook here. This is a standard result. If you have an elementary abelian locally compact group, it consists of a direct product of some copies of cyclic group order P and a direct sum of some more copies of the cyclic group order P. So this is very straightforward. And the corollary is that, well, if we have one of these characteristically simple groups, as soon as it has torsion, we know that one of these subgroups consisting of the elements of order P has to be the whole thing. And therefore, it's an elementary abelian group, and we know what it looks like. And to realize it as a monolith of something is not that hard. So you can, for instance, think of this group Cp to the n as being the additive group of a field, and then you stick on the multiplicative group as its automorphism group. You can do something similar with the other ones. I'll just point out this is maybe the most interesting one. If you have Aleph naught direct product and Aleph naught direct sum, that's actually the same as the additive group of the field fp double brackets t. So it's a very natural kind of abelian group to consider. Okay, so then we've sorted out the torsion case. And so from now on, we can assume that our group is torsion-free. That is, every element has infinite order. So then the next question is, do the elements generate subgroups with compact closure? In which case we call it a compact element. And then we write P of A for the set of compact elements, and then I write A circ for the connected components of the identity. So, so these are both closed characteristic subgroups of any abelian group, any locally compact abelian group. This isn't hard to show. And standard result about the local structure of locally compact abelian groups is that you have an open subgroup of the form R to the n plus k, where k is compact. Okay, so what does this mean? Well, if G is connected, then this has to be the whole thing because connected groups don't have proper open subgroups. So then we have R to the n plus P of G, and then P of G is compact in that case. And on the other hand, if G has trivial connected component, then this R to the n dies. And then if P of G is also trivial, then this K dies. So we have a trivial open subgroup, and that means that G would have to be discrete. So these are two cases where we know quite a lot about the group. Okay, so let's consider the case where the periodic subgroup is trivial, sorry. So no element lives inside a compact subgroup. So if it's connected, the only possibility is R to the n, and that's certainly a monolith of something. The other possibility is that it's totally disconnected, in which case we've already said it's discrete. And then the fact that it's torsion-free means that these subgroups NA are all non-zero. so they have to be the whole group. And that means that actually NA equals A for every N. So it's a divisible group. Every element has an nth root for every N. And abelian divisible groups have been classified. And the torsion-free ones are just direct sums of copies of the rational numbers under addition. So that's a standard classification we can appeal to. And then it's easy to see that these are characteristically simple. Okay, so this is in the decision tree. This is connected no, periodic yes, connected no. Sorry, no, that's not right. Periodic no, connected no. Okay. All right. We get another family by something that shows up in pretty well any talk about locally compact abelian groups, Pontryagin duality. So just a quick reminder, you take your locally compact abelian group and you consider all homomorphisms to the circle group and give that the compact open topology. And then this is called the dual of G. And because we're thinking of characteristically simple groups, it's worth saying that the duality also extends to homomorphisms. I guess it's functorial if you want to be fancy about it. So if you have a homomorphism from G to H, then you get a dual homomorphism from H hat to G hat, which means in particular that if you have an automorphism of G, you get an automorphism of G hat. It's sort of reversed multiplication. Being characteristically simple is preserved by Pontryagin duality. Various properties, we know how they behave under duality. So discrete corresponds to compact on the other side. Torsion-free corresponds to densely divisible, so sort of a dense set of divisible elements. And trivial periodic part corresponds to connected. And I'll just say that for compact and discrete groups, being densely divisible is the same as being divisible. Okay, so if we start with direct sum of kappa copies of Q, then Pontryagin duality gives us the dual, which is the direct product of kappa copies of Q hat. I don't really want to say what Q hat is. It's not a particularly nice group, but it's a natural thing to consider, the dual of the rational numbers. And we don't actually get any more examples this way because it turns out all the other families are self-dual. So if we take the standard thing we had about divisible abelian groups, divisible discrete abelian groups that were torsion-free, and then just throw it through Pontryagin duality, what we end up with is that the divisible torsion-free compact groups, compact abelian groups, are just Q hat kappa. These are also connected, incidentally, because they're dual to something that has trivial periodic part. Yeah, so if you have a connected compact abelian group, it's not hard to show that it's divisible. What we have is the following. If we have a connected torsion-free abelian l.c.s.c. group, and the periodic part is everything, then well, first of all, it has to be compact because it's connected. So we've killed off the R to the N part, and then we're just left with this compact thing. And then we conclude from here that it's actually Q hat kappa. Okay, so a bit of a word about these things being monoliths. So there's a paper from the 50s by Philip Hall that shows that if you take counting many copies of Q, that does occur as the monolith of a finitely generated group, and you can make it soluble of derived length 3. But if you only take finitely many copies of Q, then you can't make it the monolith of a finitely generated group. There's sort of an issue that happens in terms of the prime divisors, basically, of the elements. So that means this Q to the n doesn't appear as a chief factor of any compactly generated l.c.s.c group. So you can generalize the argument fairly easily. And then you feed it through Pontryagin duality and say, well, okay, Q hat to the n also doesn't appear as a chief factor of a compactly generated group. This summarizes what we get. It's definitely a monolith of something, but if we want it to be compactly generated, then we have to take kappa equals L(f)0. We can't have finitely many copies of Q. Okay, so so we come on to the last. How am I doing for time, by the way?
It's about 4 or 5 minutes.
Okay, that's fine. So the last case is the one that I couldn't find a sort of standard classification literature, which is that we have a torsion-free group, it's totally disconnected, and the periodic part is everything. So then it's straightforward to see this is a ZP module, where ZP is the p-adic integers. And if you have a compact torsion-free ZP module, it's just a direct product of kappa copies of ZP. That's a standard thing. And in particular, these things are all free as modules, if you like. But these things are not characteristically simple because you have P times the whole thing as a proper closed subgroup that's characteristic. This is not the answer, but we can go from here and build something by adding roots to this. So the easy case is if kappa is finite, you see that having PA be a submodule, it's also got to be closed and dense, and then it ends up being everything. In that case, we just get the divisible extension of ZP to the kappa, which is QP to the kappa. Okay. Now, so the interesting case is when we have a group that's locally isomorphic to the direct product of countably many copies of ZP. And we could just try taking the divisible extension of this, but that ends up being too big. So this group, this ZP L(f)0 tensor Q is not second countable anymore. So we have to take something a bit smaller, and the candidate group to consider is the set of all functions from the natural numbers to QP, such that all but finitely many values are in ZP. And then this has naturally got a copy of ZP to the L(f)0 as a compact open submodule. It's densely divisible without being divisible. And it's an interesting group for various reasons. People have suggested it as a sort of p-adic analog of separable Hilbert space. And the interesting thing is that this is the only group you get of this kind. So you have a torsion-free, totally disconnected, second countable, locally compact ZP module of infinite local rank, such that PA is dense in A, then it has to be this thing. And the argument is basically that So first of all, you show that the divisible elements are actually dense and a ZP submodule. And then basically you find a map from the minimal divisible extension of A to the minimal divisible extension of QP aleph naught that sort of takes a basis to a basis. And we construct the basis by basically Gaussian elimination. So it's sort of Gaussian elimination over an infinite matrix, but it all makes sense without getting into too much detail. Okay, so that's the classification. And just to finish, we can now sharpen some of these theorems from the introduction. So if we have a compactly generated locally compact group there with no non-trivial compact or discrete normal subgroups, then all but finally many of the minimal closed normal subgroups are FP double brackets T, R to the N, or QP kappa, because these are the only abelian chief factors that are not compact or discrete. And you can actually get them to occur, you can get each of these to occur 2 to the aleph naught times. So this is sharp. And for the chief series thing, we can say a bit more about if you have a soluble normal factor of a compactly generated locally compact group. So then each of the factors, we can split it up. So each of the factors is compact, discrete, or one of these chief factors that's not compact or discrete. So again, FP double brackets T, R to the N, QP kappa. And we know that all of these can occur as chief factors. Okay, so that's what I had to say. Just leave references. Thanks.
Okay, thank you, Colin. Are there any questions for the speaker? A completely naive one for me. You have this kappa cardinal appearing everywhere. Can they be big infinite cardinals? And if so, do you get some strange set theory things happening? Or
no, and this is why I assumed that all the groups are second countable, because I didn't want to deal with that kind of thing. So no, kappa is always going to be either finite or aleph naught. Yeah.
Okay, if there's no more questions, then let's thank Colin again. And the next talk is in 8 minutes.